Hi, I'm Andrew. We're talking about DESI. So we pretty much all know the situation. We've got six parameter standard model. We've got six parameters measured extremely well by observations such as the Planck satellite. We're all pretty desperate for something new. We've had the standard ΛCDM model for 2 decades. And so we're grabbing hold of anything that will tell us something that might take us beyond that in the hope that we can understand some of its parameters a little bit better than we currently do. So there have been two things dominating recent discussions for quite a while now. The Hubble tension has been invoked as a possible source of new physics. Not talking about that today. Today we're talking about the new results coming from the DESI collaboration, the tantalizing suggestion of evolving dark energy. DESI is the first of the stage 4 dark energy survey projects. We'll no doubt be hearing a lot about it at this meeting. The particular results under discussion today are the first year baryon acoustic oscillation observations, bunch of different tracers heading from relatively low redshift with galaxies up to high redshift with the Lyman alpha forest. But in order to get any really interesting results, DESI alone is not good enough. DESI has to be combined with other things, particularly the Planck microwave background anisotropy data is very important, and also supernova data. And in their analysis, they make different possible choices amongst the supernova data sets that are available at the moment. And that gives us some so-called tantalizing suggestions of evolution of dark energy. That would obviously be a new parameter to throw into the cosmological model, which gives us a better chance of trying to understand what might be going on in the dark sector. So for context, everything I'm going to talk about is just going to be for the so-called CPL or W0WA CDM model. This invokes an equation of state W, which varies linearly with scale factor, eventually reaching the value W0 at the present day. This slide is just taken from the paper that Marina Cortez and I wrote, and most of this talk is based on that paper. It came out very soon after the DESI results were announced, with just a couple of updates at the end for things that have happened since then. So it's just to define the terminology, and in particular, an important point is to say that any regime where the equation of state is less than -1 is known as the phantom regime, and there are quite a lot of difficulties in making physical models that cover the phantom regime. Problems with instabilities if we try to cross from a regime which is phantom to one which is non-phantom. So most results are going to be about that, but a first big clue to what's going on comes from the analysis that DESI make of a model with a constant equation of state, constant W, where they find results which are completely consistent with the ΛCDM model. So for example, using the Pantheon plus supernova data set along with the DESI data and the CMB, we get a number extremely close to the -1 of the cosmological constant model, 0.997 plus or minus 0.025. And this is already going to be quite a big clue as to what's going on. It's only when you move to the W0WA plane that you start to see something that looks more interesting. And this is from their paper. There's a lot of stuff to look at here, but I'm just going to draw your attention to a couple of things. In the left-hand panel, it's important to notice that the DESI BAO on its own does not give any very strong indication against the ΛCDM model. ΛCDM is where the vertical and the horizontal lines cross. In the crosshairs, it's well within the 2 sigma limits of DESI BAO on its own. So as they remark in their paper, it's only when you combine with other things that you start to see interesting results. And the left panel concentrates on different additions of one data set to DESI BAO. And the most interesting here is probably the CMB in purple, which shows then a slightly more than 2 sigma deviation from ΛCDM. But the main results come on the right-hand side, where we see for each of 3 possible choices of supernova data sets, certainly not independent, so we have to choose one or other to really focus on. We see a result which is now stretched quite some way away from the ΛCDM case, giving a result advertised as roughly 3 to 4 sigma, depending which supernova compilation is being used to look at the analysis. So what's going on here? Well, one of the things that Marina and I are emphasizing in our paper, which is also discussed in the DESI paper, is that you can learn a lot just by looking at the pivot scale of the dark energy. So when you have a linear equation of state, like the one we have here, you have a reparameterization invariance. You've got an amplitude and a slope, and you can specify the amplitude on it at any value of the scale factor you like. But of course, you can try to make a wise choice of that, and in order to get the simplest interpretation of the data. And in particular, you can always find a scale factor, pivot scale factor, which decorrelates the measurements of the slope and the amplitude now being called WP. So this is the pivot scale. It's been around for a long time. It was used a lot and popularized in the Dark Energy Task Force paper of Albrecht et al. In 2006. The figure of merit uses it, but the important factor is this decorrelation. Importantly, the pivot scale is telling you where the data is actually really constraining the equation of state best. And so the DESI paper quotes the pivot redshifts. If we choose the Pantheon Plus or DESI Year 5 supernova data sets, it's 0.79, it's 0.75 for the Union 3 data set. In any of these cases, it's not really the supernova that's the main driver here. The CMB data is the strongest data, and it's well known that the CMB data fixes the angular diameter distance to last scattering, and that corresponds to a pivot scale in CPL models of around this value of the pivot scale, somewhere around 0.7 to 0.75, I think is the number. And the other data sets give some correction to that. So the main constraints on the equation of state are coming from around these redshifts. First point is we've decorrelated the uncertainties on the amplitude and the slope. What that means is that the constraint you would get on W at the pivot scale is going to be extremely close to the constraint you get if you assume W is constant. So you're now pivoting around an amplitude which is fixed. The slope is changing, but the amplitude is fixed. So you inevitably get the same amplitude as you get for a constant W model. And indeed, the uncertainty, at least in the Gaussian approximation, is unchanged as well. So it's as if the slope plays no effect in how well you constrain the amplitude of the equation of state at the pivot. Now, this is their results. We see two surprising things, I think. So the first one is that the ΛCDM model is quite significantly away from the best fit region, and that the best fit region is where we have phantom behavior, where W is typically initially less than -1, as we'll see in the next slide. The second surprising thing you see in this plot, or thing that you should notice when you see this plot, is that the contours are extremely elongated, and the direction in which the contours point to is very much towards the ΛCDM model where the crosshairs are. Now, that's no coincidence, because the orientation of the contours is telling us about the correlation, as I've just mentioned, and about the pivot scale. So let's put on some lines to try and understand better what's happening. So the first thing is I've put on a red line and a purple line just to indicate where the different phantom regimes are in the model. So we've got two possibilities. The model can be phantom initially or not, and it can be phantom at present or not. And when you combine these two possibilities, it divides the plane into 4 sectors. Up at the top right is the region where you're never phantom. W is greater than -1 at all times. Bottom left, you're always phantom. But all of the data lives in a region where you're initially in a phantom regime with W less than -1 and make a transition into a non-phantom regime by the present. The pivot scale is important because the corresponding redshifts, 0.26 and 0.33, can find a line in this W0 WA plane which corresponds to having an equation of state equal to -1 at the pivot scale. And for the blue and green data sets, that's the blue line drawn here for its pivot scale factor 0.79. For the Union data set in orange, it's a slightly higher redshift, and so the line is tilted slightly more. What you see is that these lines follow quite accurately through the data set, and that's telling us that if we make a transformation to the pivot scale, which involves sliding horizontally the points on the blue or orange line onto the red line, so turning it towards the vertical, you drag the contours along with you, it will drag these contours to where W at the pivot scale is close to -1, as I've already remarked, is what we see in the constant W model. What we're seeing is these data is that there's quite a bit of coincidence going on, and unexpected behavior and coincidence. These are the actual W of A of the best fit models for the 3 different choices of supernova data set. There's a fairly mild spread, but in each case you see that the W starts much less than -1 on the left-hand side, and it crosses -1 relatively close to the present and then goes into the non-phantom regime. Now, there's no actual data right at the present or at very early times. So the main data is constraining us around the pivot scale, and the blobs show what the value of the equation of state is at the pivot scale. And as advertised, it's very close to the cosmological constant case of -1. So what we have here is a kind of a coincidence. Marina and I have called it the phantom crossing coincidence or phantom X coincidence, that the W almost all the time is not close to -1, but it crosses -1, and it does so just at the redshifts where the observations are at their strongest. And there's no reason why that should be so. This is a new coincidence. It's different from the coincidence problem of dark energy, and it's different from the original cosmological constant problem as well. An equivalent way to state the coincidence that might be more visual is that it's saying that the dark energy attains its highest ever value within the window where the observations are being made. Because in a phantom regime, you have the dark energy increasing. Then when W reaches -1, it turns over to the constant value of the cosmological constant model. You go into the non-phantom regime, it starts to decrease. So the dark energy density that corresponds to these lines is a sharp peak, and the peak is located at the redshift where the observations are being made. So in two ways, the best fit models are appearing in a surprising region of parameter space. They're in the phantom regime with the phantom crossing coincidence as well. And because of that, we're in a situation which is a little bit awkward. Lots of people want lambda CDM to be wrong because they want new physics, they want new clues as to how the universe works. So you find lots of people being very happy that lambda CDM is under a lot of pressure, apparently, from this data. But it's not nearly so easy to find people who are cheering along because they found that their favorite model is a very good way of explaining this data. Generally speaking, there aren't a lot of models in this area of parameter space before the data came along. I mentioned just briefly, in case it comes up in discussion later, we're concerned about the full range of the DESI prior and how wide it is. This is the full prior which they use. It cuts off in the top right-hand corner to ensure that there's early matter domination, which of course the data are bound to require in the end. But otherwise, it's extremely broad. The plots of data that you've seen so far live in this corner in the middle here. But I just wanted to draw your attention that a clear majority of the parameter space is in the phantom regime, and a big sector of it is in the always phantom regime, which is very poorly motivated on physical grounds. Coming towards the conclusion, I just want to comment on two more recent papers that came out from the DESI collaboration after Marina and I wrote our paper. And there's a paper by Calderon et al., and they do something that's very useful indeed. They model the equation of state W of A instead of with just the CPL parameterization or W naught WA, use a four-term Chebyshev polynomial expansion. So this is moving towards allowing a more general functional form for the W of A. So they draw a conclusion which sounds a lot like the original CPL conclusion. I'm not so convinced their data really support that. And here's figure 1 from their paper to have a look at. So the top row is the equation of state behavior, starting just for DESI BAO, then adding supernova, and then the full 3 data sets on the right. The lower plot shows the corresponding dark energy density as a function of redshift. So you see, for example, in the left-hand side for DESI BAO, you see a strong phantom crossing round about where the observations are. In the lower plot, you see a very strong peaking of the energy density that corresponds to that phantom crossing. Something does puzzle me a little bit about this figure, maybe it's a good thing for the discussion later on, which is that for the W naught WA model, there wasn't much of a signal in DESI BAO alone, and it became reinforced when we added in the other data. In these plots, the reverse seems to be true. If you look at DESI BAO on its own, you see very strong evolution of W of Z through the observed window, and it's still perhaps only 95% or just a little bit greater, but nevertheless, it's quite a strong evolution. And when you add more data, that strong signal largely goes away. So the very strong peak in the dark energy you see in the lower left plot is much weakened once you add in the other kinds of data. So that trend seems to be rather the opposite of the trend that's implied in the original DESI W naught WA analysis, where DESI BAO on its own was not giving the strongest result. Then, more recently, a DESI collaboration produced a paper by Liddle et al., where they consider what they call physics-motivated models for evolving dark energy. They class them under these 3 kinds: thawing, immersion to Mirage. I'm just going to comment briefly on the Mirage models. The Mirage models are ones which give the same angular diameter distance to last scattering as does lambda CDM. So those are models which automatically give the same CMB predictions as lambda CDM model does. Now they just correspond to a line in the W naught WA plane, and because I've already remarked the pivot scale of the CMB is what's driving the pivot scale of the data generally, it's unsurprising that these Mirage models are on a line very similar to the lines I drew earlier for how the pivot scale evolves. And naturally, they run through the middle of the data. So we see that here. This is the Mirage class. And again, the same kind of general trend that the DESI BAO on its own on the left seems to give a stronger signal than when you add in more data. And by the time you get to the right-hand side with all 3 data sets, the curve is more or less horizontal and looks a lot like the lambda CDM. Nevertheless, they go on to report Bayes factors for the Mirage class of models and remark, in fact, that they see moderate evidence in favor of the Mirage class over the ΛCDM. I certainly want to take issue with that statement because I like Bayes factors a lot, but there's two things I feel are a little unsatisfactory with that. One is about the prior. To say that this favors the Mirage models is implying that before the data came along, the Mirage models should be thought of as likely as the ΛCDM models. I don't think anyone thought that. ΛCDM models are a priori much more likely, especially as there's no theoretical motivation for the Mirage models. It's an observational coincidence to arrange the last scattering surface to be the same. But I think probably more important to remark in this is that there's a kind of cheating because the Mirage models have been chosen specifically because they fit the data well. And if you've already used the data to motivate your choice of models, it's a kind of double counting to then compute a Bayesian evidence and claim that the Bayesian evidence is then supporting your model. You know, it's a bit like you just select the best fit model after the event and then compute the evidence to say, oh yeah, the best fit model does much better than all the other models. So I'm doubtful that this Bayes factor analysis is really giving much evidence in favor of these models. To conclude, the DESI result is interesting, but it's also unexpected in two ways. The best fit models are phantom for most of the evolution, and indeed the bit of the models which are non-phantom, there's probably very little data there. It may be largely built in from the extrapolation of the CPL model into a region where there isn't much data. And there's this big coincidence that the models are crossing from a phantom regime to a non-phantom regime just at the window where we happen to be observing, and that's quite mysterious. One possible explanation of that is that the DESI prior has a lot of phantom models in it, which is not well motivated by physics before the data came along. And to remark, if we imagined altering the analysis to downweight the phantom models so that many more of the models were non-phantom models, that would certainly weaken the phantom crossing coincidence quite substantially, but it would also significantly reduce the significance of the evolution detection as well. So when you try and resolve one, you lose the other. The two are tied together in that way. Finally, definitely something that everyone may want to discuss in the discussion session for this talk is that it appears to me that the subsequent DESI collaboration analyses, the two that I've just remarked upon, somewhat weaken the case for evolving dark energy as compared to the original paper, but other people may well disagree with that. Let's see. Thanks for your attention.